Hi everyone, this is Mrs. J, and today we're going to talk about areas, distances, and the definite integral. So first I want you to imagine a scenario where I ask you to find the area under this curve represented by f of x from x equals a to b. So if you look at this shape, this definitely doesn't look like a shape that we learned about in geometry, right? This isn't like a rectangle or even a trapezoid where there's a general formula for this type of shape. So to find this area, we would have to use a different approach. So we're going to start learning about some of those different approaches today. So eventually we will be using calculus. We'll use integration to help us calculate the exact area under a curve. But first, we have to work our way up. So we're going to start by using what's called the rectangle approximation method. So since we don't have a general formula for this shape created by the curve, we're going to use shapes that we do know how to find the area of, and the easiest one for us is rectangles. So imagine, you draw rectangles under your curve, and then we find the area of those rectangles. It's a general approximation of the area under the curve. It's not going to be perfect, so that's why it's an approximation. So we can do three different setups for these. You can use the left endpoint. So you'll see here that the left side of our triangle is on the curve, and then that dictates the height of each rectangle. Or you can use the right endpoint. So you can see like here, the right endpoint is on the curve. And again, that will dictate the height of each individual rectangle. Or you could use the midpoint. So you can see in here, the midpoint of each rectangle is on the curve. So depending on what your curve looks like, sometimes one approach is better than others. So again, sometimes it will over approximate and sometimes will under approximate. So sometimes you have to be strategic in which one you decide to use. Okay, and as I just mentioned, sometimes depending on the method we use, it over or underestimate. So just be aware of which one you are using. So if you look at this example, the area under the curve, this is the exact area. It would look like this. But if you look at the two, a left hand and a right, a left endpoint and a right endpoint rectangle method, you could see that, well, for this particular graph for x squared, if you use the right endpoints, we actually would get an overestimate, because you can see that there's these areas from your rectangle that are above. But if you use the left endpoints, you definitely get that underestimate. So again, it's not necessarily good or bad because this is all just an approximation. It is just important to be aware of whether you have an over or an underestimate. All right, so first we're going to try to get an approximation of the area under this curve, 16 minus x squared, from 0 to 4, using first a left endpoint approximation. So first, we can decide the width of each of our rectangles. Just to make it easy, let's set each width equal to 1. So we're going to have 4 rectangles. Again, since we're using the left endpoint, every time we find the left top corner of our rectangle, it should be on the curve. So this rectangle will look like this. This rectangle will be here. And then for the next one, again, the left endpoint should always be on the curve. And then for the last one, it will look like that. And so now we're going to find some useful coordinates that we can use to help us find the areas of the individual triangles. Or rectangles, sorry. So first, we know that we do have one endpoint when x is 0. And so we want to figure out the height of our triangle, which is simply the y value when x is 0. So we see that that's at 16. And then if we want to find the height of this rectangle, that's when x is equal to 1. So that'll be 15. And then we want the height of this rectangle, which is when x is 2. So that'll be 12. And then here we want the height that will be dictated when x is 3. So that is a height of 7. So now we know the heights of each of our rectangles, and we know each of the widths is just 1. So now we can calculate our left endpoint approximation. So for this, we can say L4 just to denote that it's a left endpoint and there's 4 rectangles. So for the first rectangle, again, the width is 1, so 1 times the height, base times height, and our height is 16. And then for the next one, our base is 1 and our height is 15. And then our base is 1 and our height is 12. And then for the last one, our base is 1 and our height is 7. I know it doesn't make a whole lot of sense for this problem to write this in this way, but just we can see that it's just whatever our width is times the sum of our heights, right? And again, we don't need to show this because you guys know that these two things are equivalent, but I'm just trying to show you that it's the width times the sum of the heights. So then if you actually make this calculation, we'll see that this approximation is just 50. So we should make a note. We can see for this one that this is definitely an overestimation, just based on what our graph looks like. But next we're going to try one from the right side and we can compare. Okay, so let's try that same thing again with but use a right endpoint approximation. So that means for each rectangle, the height is going to be dictated by the right side. So the first one should be when x is 1, so it will look like this. Here's my first rectangle. And then I look here, here's the height. The height is on my curve. The right side here is on my curve. And then for the last one, this will look a little bit strange. On my curve is at 4, so it's actually just flat. There is no visible rectangle there. So now we're going to find those heights again. So the first rectangle is the height is when x is 1, so we know that's 115. And then we have 2, 12, 3, 7, and then 4, 0. So we can denote this one with, we'll do R4, again, because it's a right endpoint approximation and there's 4 rectangles. So we have the width. So we have the width 1 times height plus the width times height, width times height plus the width times the height of our last rectangle. And again, this is just our uniform width times the sum of our heights. And if we do this calculation, it is 34. So that's our approximation for the area under that curve. So we can see, again, based on the picture, that this is an underestimate. You can see it is significantly lower than our last estimate, which was 50. So last for this curve, we're going to try a midpoint approximation to see what we get. So again, this time, the height of each rectangle is going to be dictated by the midpoint of each interval. So if I still want to split it up into 4 equal rectangles, that means that this height, or my first rectangle, will be dictated by f of 1/2. So whatever it is halfway through, so it'll be right there. There's my first rectangle. So again, we're doing the midpoint between 0 and 1. And then we'll do the midpoint between 0 and 2, which is 3/2. So whatever that height is on our curve, that's where our rectangle will be. And then the midpoint of 2 and 3, so at 5/2, that's going to be the height of our rectangle. And then 7/2 right here. Okay, and to help us find those heights, we will plug in 1/2, 3/2, 5/2, and 7/2 into our function. So you'll have to do a little bit of math for these, but I have the values worked out. So we have 63/4, 55/4, 39/4, and 15/4. So those are the heights at each of our individual midpoints. Now, when we go to calculate the area, we can say M4. The rectangles they're still uniform in width, and all of the bases are still 1. They have a width of 1, so we could do the base times the sum of the individual heights. So 63/4 plus 55/4 plus 39/4 plus 15/4. So that gives us 172/4, which is 43. So this one, again, we can see is probably the best estimate for this particular shape, because for each rectangle, we see we have a little bit above, but then a little bit below. So I think for a curve like this, if I was given the option, the method that I would pick would be the midpoint approximation. All right, so now I want to kind of write the general forms of what we were doing for each of the different approximations. So for our left endpoint approximation, I'm going to say Ln, where n is just the number of rectangles. We always did delta x, so that's the kind of the width of each of our rectangles, assuming that they are uniform width. And just note that we can find that if they are equal widths, we could just do b minus a over n, where b is kind of the right boundary, a is the front boundary, and then n is the number of rectangles. So we can find, we did delta x, and then we multiplied it by the individual heights. Now for this one, since it was the left endpoint approximation, we started at f of x sub 0, and then we did plus f of x sub 1, plus, and then we added up the however many, and then we would end with f of x sub n minus 1. So if you kind of go back to that first one we did, our last rectangle was dictated by f of 3, even though it was from the interval 0 to 4. And again, that's because we were using the left endpoint. Now, a more general way to write this, since we're taking the sum, we can do our summation, and we can say from I equals 0 to whatever, n minus 1. So again, that last coordinate, the last x value is always 1 less than our right side endpoint. And then we'll say f of x sub I times delta x. So again, it's just the height of our rectangle times the width of our rectangle. So that's kind of the general form for our left endpoint approximation. Now for our right endpoint approximation, we still did delta x, but remember for this one, we started at x sub 1. Even though our interval started at 0, we start on the right side, so that's when f of x sub 1, and then we did f of x sub 2 plus dot dot dot, and then we actually for this one ended at f of x sub n. We actually ended at our right endpoint for our rectangles. And then if we want to kind of generalize this in summation notation, it's from I equals 1 still to n, and it looks exactly the same. Except here, again, we're starting at 1 instead of 0, and we are ending at n instead of n minus 1. So everything is kind of just shifted over to the right one. And then for our midpoint approximation, so we can say m sub n, we still have delta x, and then we have times the individual heights. So for this one, I'll say f of, so we did x sub 0 plus x sub 1 over 2. That's the midpoint between 0 and 1. And then we plug that into our function, plus, and then I'll kind of skip the middle ones because it's a lot of writing. And then for that last one, we found the midpoint between our second to last term and our last term, and then divided by 2. So we did, remember we did the midpoint between 3 and 4 and divided by 2. So again, this is just a general form. And then if we want to write this in summation notation, we'll say from I equals 1 to n, and then we'll say f of x sub I minus 1 plus x sub I over 2, and then still delta x. So again, it's just saying the midpoint between the two, any two given intervals, and then divided by 2. So this is kind of the general form of each of those that we can apply. And then a few extra notes below. There's different ways that we can, you can be given a problem. It is common to see a graph, an equation, but I'd say the most common, especially on the AP exam, would be a table of values. So we're going to try one of those in just a second. Again, if the rectangles are equal widths, we can find the change in x delta x, which again is just the base of our rectangles, by doing b minus a over n, if we're finding the area of the curve between x equals a and x equals b. But I do also want to point out that the rectangles do not need to have equal widths. I think it's a common strategy to use, but maybe sometimes it's easier to dictate the width of each rectangle based on the curve. I also want to point out if you have a given table with unequal widths, you do need to calculate the area of each rectangle separately and add them together, so you can't do just the uniform widths by the sum of the heights. And also it's really important that we are not making up data anywhere along the way. So you just can't make assumptions about what you think values are. You can only go based on what you see in the table. And then last, this is something that we will be working with in just a second. If v of t represents the velocity, then the area under the curve is actually the total distance traveled. So if you think about why that's occurring, I want you to think about distance equals rate times time. And remember, rate is essentially the absolute value of velocity. So here's our velocity, and again, it's in terms of time. If you think about, we use one of those rectangles to find part of the area under the curve. This is time, and this is your rate. So the distance equals the rate times the time, which is essentially one of those rectangles. Again, because the x value represents time and the y value represents your velocity. So just a few extra things to note when we're working with these types of approximations. All right, so let's look at this next example. This says speedometer readings for a motorcycle are given in the table below. Find an upper estimate for the distance traveled by the motorcycle during this time period using the velocities. And then we're going to compare this with a midpoint estimate. So again, here's our velocity. So we know that the area under the curve, again, is really the total distance traveled. So first I want to get just an idea of kind of the shape of my curve. So I'm just going to plot some points really quick. Again, super rough sketch. So if we had 0, 22, and then we have, here's 12, 12, 24, and then we have 24, 25, and we have 36, 28, and then we have 48, 30. So our curve would look something kind of like this. So we see it's increasing. So here, if they want us to find an upper estimate, we could see that we should use a right endpoint approximation, because then our rectangles would look like this. And there you go. And you can see that we were actually given the data. Our x values are uniform, so we could see that the width of each rectangle is 12. So now we just need to calculate our right endpoint approximation. We are just going to use 4 rectangles just because based on our data, that will be the easiest way for us to split up our rectangles. So here our first width is 12. Well, all of the widths are 12. So we can do 12 times the sum of the individual heights. So we're going to be using these heights because again, it's the right endpoint approximation. So 24 plus 25 plus 28 plus 30. And then, so that gives us 12 times 107. So our total distance traveled will be 1,284 feet. Okay, so again, that is an overestimate. And then they want us to compare that to the midpoint estimate. Now for this one, again, it's really important that we don't just make up data. So if we wanted to take we can't actually use the midpoint between 0 and 12 because we don't have information about the velocity when time equals 6. So just because it's the midpoint between 0 and 12 doesn't mean we can just take the midpoint between 23 and 24. That's not how it works. So again, we cannot make up data for in between here. So that means that we actually have to just make use of the data we have. So if we want to use the midpoint, we're actually just going to need to use 2 rectangles because we can do the midpoint. We know the midpoint between 0 and 24 because we have the value for 12. And we know the midpoint between 24 and 48 because we have the value for 36. So this is what our midpoint triangles would look like in blue. That again, here we would only have 2 triangles to work with. So here, the width of our, 2 rectangles to work with. So here, the width of our rectangle is 24. And then we are going to use the height at 12. So we'll use this height, and we'll use the height at 36. So times 24 plus 28. So 24 times 52 is 1,248. So you might be noticing that we actually get the same approximation from both methods. So maybe you're wondering, well, how could that be? It looks like the midpoint method is a little bit more accurate. It's because with our right endpoint approximation, although we know it's an over approximation, we have 4 rectangles compared to only 2. So you can kind of see that means that the more rectangles you have, the more accurate you're going to get. Because again, we can see for this curve, a midpoint approximation should be more accurate, but because we have fewer rectangles, it decreases that accuracy level. So how can we go about getting a more accurate approximation using rectangles? Well, the more rectangles we have, the more accurate our representation will be. And then the way we increase the number of rectangles is essentially decreasing the width of each rectangle. So you can see as we decrease the width, the number of rectangles increases and it looks closer and closer to the actual area under the curve. Now, the most accurate height of a rectangle is typically not just at a left endpoint or a right endpoint or even at a midpoint. So just in terms of some terminology, whatever x value we use to determine the height of our rectangle within the individual interval or within the width of each rectangle, we can call those our sample points. So you can see here, this sample point at x sub 1 is not a left endpoint, it's not a right endpoint, and it's not a midpoint. So again, it doesn't have to be one of those things. Those are just typical ways that we will calculate. So as you saw on the last page, as our width gets narrower, the number of rectangles increases, and ideally the number of rectangles would approach infinity. So of course we're going to go back to limits here. So notice that we can write this area of that region under the curve as the limit as n approaches infinity. So this is the number of rectangles. So again, the more rectangles, the more accurate the limit. And then we have our rectangle approximation with the number of rectangles here. So again, it's the limit as n approaches infinity. And then we have f of x sub 1 times delta x plus f of x sub 2 times delta x. So notice that each of these are simply the height of the rectangle, and delta x right here is simply the width of our rectangle. And notice here, since they are all delta x, we are assuming that there is a uniform width. So we do know that there's a uniform width when we are expressing it in this way. Although we know if we want to use a method where each rectangle has a different width, we have to do those individual calculations by hand. All right, so this process of using rectangle approximation, we can call this a Riemann sum. So when we're taking the sum of all of those individual rectangles that are found by f of x, well, our sample point times delta x, which again is the width of each rectangle. Again, this is called a Riemann sum, and we know that it is an approximation. Sometimes it's an overestimate, sometimes it's an underestimate. And look, we can see that it's not perfect, but it's kind of close. Now, if we want the exact area under a curve, we're going to be using a definite integral for this. So we're going to talk more about this definite integral process now, and again, that's to get the exact area under a curve. All right, so here we have the technical definition of our definite integral, and it's over the interval a to b with n subintervals. So you can see here we have our definite integral. Remember this kind of S shape, this little symbol right here, that's our integral symbol. And this is our lower boundary and our upper boundary. So you can see that our definite integral is equal to the limit as n approaches infinity of our Riemann sum. So here's our Riemann sum, and remember n represents the number of rectangles, so it's the limit as n approaches infinity. So this is, again, our technical definition of a definite integral. All right, so now we're going to try expressing a definite integral as a Riemann sum. And for this one, we're going to use right endpoints. And we're not actually going to evaluate the limit, we're just going to practice the notation. So first, we want to look at, here's what the general form of a Riemann sum looks like. F of x sub I times delta x. So I want to remind you that this is just the height of each rectangle, and this is the width of each rectangle. Now we can always find delta x by doing b minus a over n. So in this case, our b value is 3, and our a value is 1, and it's over n. So that means that the width of each rectangle is 2 over n. Now, just to kind of visualize what's happening here, and again, since we're doing a right endpoint sum, let's say here's our curve, and this curve is e to the x, so that's their function. And let's say here's 1, and let's say over here is 3. Now, since we're doing a right endpoint approximation, we know that we actually need to figure out how would we define this height right here. So if this is the right endpoint of our first rectangle, like this, and we know that the width of our rectangle for this example is 2 over n, this would be 1 plus 2 over n. And then let's say if we add another 2 over n, this is what our rectangle would look like. This is 1 plus 2 over n times 2. And for our third rectangle, right, the x value that we use would be 1 plus 2 over n times 3, right? So for each rectangle, we have to add 2 over n however many times. So for the first rectangle, we added it once. For the second rectangle, we added it twice. For the third rectangle, we added it 3 times. And again, that's because we're not actually starting at the height when x is 1, we're using a right endpoint. So we're starting at the height when x is 1 plus 2 over n. Now, the way to denote that is we can see as we progress through each rectangle, we're going to multiply 2 over n times I. Whatever your I value is, that's how many widths we're essentially going to add. So when we write our Riemann sum, we say the limit as n approaches infinity, and again from I equals 1 to n, and here we're doing f of 1 plus 2 over n times I. So again, that gives us the height at each of these values. When I is 1, we add this once. When I is 2, for our next rectangle, we add it twice. When I is 3, we add this width 3 times, and that will give us our right endpoint height. And then we need to add in our delta x, which we already know is 2 over n. So times 2 over n. And then we can actually just go and substitute this in to our formula, because we know that the function we're working with for this one, f of x, is equal to e to the x. So we can say the limit as n approaches infinity from I equals 1 to n. And again, we're just plugging this into this function. So it's e to the power of 1 plus 2 over ni times 2 over n. and this would be the limit of our Riemann sum. So again, if you're wondering, hey, where did this 1 come from? Is this because this is 1? Remember, the 1 is always, or this value right here is always going to come from our lower boundary of our definite integral, because that's kind of our starting place when we're finding that area. All right, so let's try one more together. So here we have the integral from 5 to 9 of x squared minus 2x dx. So just like we did in the last example, we're going to start by finding delta x, or defining it at least. So delta x is going to be b minus a over n. So we're going to call it 4 over n in this case. We can do another right endpoint Riemann sum. So the limit as n approaches infinity from I equals 1 to n. And here, this time, our lower boundary is 5. So we're going to start with 5, and then we're going to add as many widths as we need. So it'd be 4 over n times I. And think of I as which rectangle you're on. So if you're on your first rectangle, you need to add 1 width. If you're on your second rectangle, you need to add 2 widths, so on and so forth. And then we do times delta x, which is 4 over n. And now all I need to do is take this and substitute it into my function. This limit is going to look a little ugly, but it is what it is. So we have 5 plus 4 over ni squared minus 2 times 5 plus 4 over ni, and all of that times 4 over n. And there you have it. So remember, with these, start by finding delta x, and then you're simply just adding that width to a multiple of that width from your starting point, which is your lower boundary here. So that 5 becomes this 5, and then you just plug in your expression into your function to expand it out. All right, so now we're going to try to do the opposite. We're going to start with this limit of a Riemann sum, and we're going to see if we can write it as a definite integral. So when we're doing this, maybe the first thing we can start with is identifying what the function is. So we can see here that we are plugging in 3 plus 5 over ni to the function sine squared of x. So we know that our function is sine squared of x. So we could say sine squared of x dx. But now we need to use the rest of the information to try to identify our lower boundary and our upper boundary. So remember, we can always find our lower boundary by looking right here. This is our lower boundary, and then we're adding those multiples of the widths of our rectangle. So this represents the width of our rectangle, so this value must represent our lower boundary. So this is going to be a 3. And then remember, the width, this is delta x. Delta x can be found by doing, remember, b minus a over n. So we know that 5 right here is just b minus a, and we know that a is 3, so we can set up a little equation if you want. We say b minus a equals 5, b minus 3 equals 5, so b must be 8. Or you could say, hey, if this is the lower boundary, and this is the difference between the upper and the lower, then it must be 3 plus 5, which is 8. So we can use this expression and this to determine a and b, and then here we have our definite integral. So I think when you look at the limit of a Riemann sum, it can look a little bit overwhelming, but if you know the specific parts to look for, it's actually not too difficult to go from this form to this. All right, let's look at part B. Again, this one does look really overwhelming, so maybe you can kind of try to pick out what's being plugged into our function. So you can see here we have the same expression here and here. So we know that the stripped down function would be 2x squared minus x. So that's the function that we're working with. So 2x squared minus x dx. And then we can look within this expression. This first constant right here is always going to be our lower boundary, so that's our a value. And then we know that right here, or here or here. This is going to be b minus a. So we could say b minus a equals 2, b minus, and we know that a is negative 2, so b must be 0. And there's our definite integral. So again, with these, I think it's really just a matter of not getting overwhelmed by a really large expression and kind of breaking it down into little parts and identifying the stuff that you know. So really everything we've looked at so far, it's just been curves that are above the x-axis, but Riemann sums and definite intervals give net area. So they give net area, which means anything above the x-axis is positive, but anything below is negative. So it will actually take away from the overall area. So it is very, very possible for a definite integral to be positive, right? If you have more above the x-axis than below, you will have a positive definite integral. It's also possible for your definite integral to equal 0. So here you can see that kind of if you combine these two positive areas, it looks like it's about the same shape and size of this negative area. So it's very possible that the negatives cancel out the positives and you end up with just 0. Or, of course, it is also possible for our definite integral to be negative. So if the area between the curve and the x-axis is larger under the x-axis than above, then our definite integral will be negative. So just remember that definite integrals give a net area where anything below the x-axis is negative. So now we're actually going to try to calculate some of these definite integrals, and we're going to do this by interpreting them in terms of area. So let's look at this first example. We want the area under the curve y equals 3, so it's just a constant function, y equals 3, from 1 to 5. So for this, we can kind of sketch it out. So again, our function is just y equals 3, so it looks just like this. Here's our curve. It's just a horizontal line. And then if we're going from 1 to 5, well, we know that this is just a rectangle, and we can find this area just kind of using geometry. So we know that the area of this rectangle will be our base times height. We could see that our base here is 5 minus 1, which is 4, and our height is constant at 3. So that area, the shaded area, again, which is what this definite integral represents, is simply 4 times 3, which is 12. There you have it. All right, let's look at this next one. Here we have a linear function, x plus 3, from negative 5 to 3. So for this one, it might be useful for us to kind of sketch a picture of what this looks like. So we know that it has a y-intercept at 3 and a slope of 1. It also has an x-intercept at negative 3, so it looks like this approximately. And then here's negative 5, and we'll say here is positive 3. So we want the area from here to here, remembering that anything below the x-axis is negative and anything above is positive. So you can see here that we actually just have two triangles, and we know how to find the area of a triangle, so we can find we can solve this definite integral. So let's start with this negative area right here. So remember, the area of our triangle is just 1/2 base times height. So we can see here, so our area, I'll call it A1 for that first area. Our base is 2, and if you follow the slope, then our height will also be 2. So this is 2, this is 2, so 1/2 times 2 times 2 is 2. However, because it's below, it is going to be negative. So far we have an area of negative 2. Again, that's for this area. And then I'll call this second triangle, triangle 2, so this will be A2. So if we look from negative 3 to 3, we can see that our base is 6, and because our slope is 1, our height will also be 6, so 1/2 times 6 times 6. So this area is going to be 18. And it is positive because it is above the x-axis. So our total area is just going to be -2 plus 18, which is 16. So again, we're just using basic area, using shapes that we know to find the definite integrals. All right, let's look at this last example here. So here, if you look at this function is actually a semicircle. So if you have this function like this, and imagine we squared both sides. So it's actually x squared plus y squared equals 4. So really this is just the positive half of a circle whose center is at the origin with a radius of 2. So it looks actually like this. So 1, 2, again, here, here, and here. If the center is at the origin, the radius is 2. These are 3 values from our, again, our semicircle. So it looks like this. And again, we just know that it's the part above the x-axis because it was just the positive square root. So we know how to find the area of a circle, and we could also, of course, find the area of a semicircle. So here our area is going to be 1/2 times pi r squared, because again, it's just the top half of our circle. So our area is going to be 1/2 times pi, and we know that our radius is 2, so 2 squared. So the area of our semicircle is 2 pi. That is the area under the curve, and therefore what our definite integral is equal to. All right, so that is all for today's video. Thank you so much for watching.